Appreciate that. It's really great to see a lot of familiar faces in the room. Yeah, it's not that long ago, I remember sitting in those exact seats, seeing talks by professionals, and really being wowed by the opportunity to sit and hear some of the projects that folks get to work on. So hopefully one day you guys will be up here telling about all the really cool projects that you've had the opportunity to do. Also saw a few familiar names on the online chat or Zoom. So yeah, thank you guys for those that I recognize for tuning in today. Appreciate that support. So yeah, today I'm going to talk to you a little bit about Spirit Lake. If y'all haven't heard of it, it's this little project we have on the Gifford Pinchot National Forest. So I'll give a brief history of the Spirit Lake outflow, then I'll transition into a discussion on engineering challenges that we've had over the years managing that outflow. And then I'll kind of conclude with a brief overview of some of our current plans with regard to trying to develop a longer term, more resilient solution to the management of Spirit Lake. So to orient you as to where Spirit Lake is, this is a map of Washington. The black dot down near Vancouver is where our office is located. And the red dot just north of Mount St. Helens is approximately located where Spirit Lake is. So the project is located on the Mount St. Helens National Volcanic Monument of the Gifford Pinchot National Forest. And that essentially means there's a few additional constraints we have with regard to producing projects within the monument that I'll kind of discuss later. So the May 18th, 1980 eruption of Mount St. Helens resulted in some very dramatic changes across the landscape of Southwest Washington. Over 150 miles of square miles of forest were destroyed. Over 150 new lakes and ponds were formed. Rivers changed their courses. The bed of the Columbia River at the Cowlitz rose by 30 feet, and ashfall reached as far as Montana. Additionally, there was a lot of property damage that occurred to hundreds of homes, bridges, and roads. Highways were closed for a week, and airlines canceled over 1,000 flights. So pretty big impact to the local area. Unfortunately, and most sadly, 57 people lost their lives because of the eruption. And even today, it's still considered one of the most disastrous volcanic eruptions in US history. And this last photo just shows some barges dredging the Columbia River post-eruption. Okay, so this video, courtesy of the US Geological Survey, is kind of a composite of multiple images taken during the eruption. I am not a volcanologist, so I will stumble my way through this, but essentially, an injection of magma at shallow depth created a large bulge on the north flank of the mountain. A subsequent earthquake caused the entire weakened north face to slide away in a sector collapse, which ended up being the largest subaerial landslide in recorded history. And I'll just hit play on this again so it keeps looping. So this allowed the partly molten rock, rich in high pressure gas and steam, to suddenly explode northward towards Spirit Lake in a hot mix of lava and pulverized rock, which overtook the landslide. Then an eruption column rose 80,000 feet or 15 miles into the atmosphere, depositing ash in 11 US states, as well as certain provinces of Canada. At the same time of the eruption, existing snow, ice, and several entire glaciers were caught up in this surge, forming a series of large lahars that reached as far as the Columbia River, nearly 50 straight air miles. It's a lot more in river miles to the southwest. It's important to note that the eruption occurred in some separate, what I'll call phases, which I'll describe a little later. And these phases had some very serious ramifications for some of the engineering considerations in managing those geohazards in the North Fork of the Toutle River. So this map, again, from the US Geological Survey, shows just how far reaching that eruption was and how far those lahars went. You can see in this image, lahars went down both the South Fork and North Fork of the Toutle River, where they converged, entering the Cowlitz, going both upstream and significantly downstream to the Columbia, where that lahar actually flowed upriver quite a ways. So a lot of energy in the system to enter into a river like the Columbia and move upstream. So the rest of this presentation really is going to kind of focus on this debris avalanche that was resultant from the eruption that blocked the natural outflow of Spirit Lake, which was the North Fork Toutle River Valley. And here where the USGS has mapped pyroclastic flow deposits, that's pretty much the entirety of the debris blockage that we'll be talking about later today that blocks Spirit Lake to the North Fork of the Toutle River. So again, focusing on the North Fork Toutle Basin, these pre and post false coupler images really highlight the magnitude of changes that occurred within the basin. Here on the left, you can see the pre-eruption image. You can clearly see a drainage coming out of Spirit Lake. You can see that there were lots of vegetation indicated by red, a lot of clear cuts showing there was no vegetation. And then post-eruption, you can see that the landscape is dramatically changed. You can see the debris or the lahar that went down the South Fork and North Fork of the Toutle. And it's maybe not so obvious in this photo on the right, but you can see that the area of Spirit Lake was increased substantially. We'll talk a little bit more about that. And then this little feature here stands out as well. I'll discuss that in a minute. Just another image, aerial image, showing what the lake looked like pre-eruption versus post-eruption. Again, I think this image really shows just how large that area changed, and there was subsequently a volume change associated with a 200-foot raise of the bottom of the lake elevation. So yeah, went up 200 feet, and the landslide or the debris blockage that ended up blocking the lake is about 500, give or take a few tens of feet thick, kind of at its maximum downstream of the lake. So I pointed out a unique feature in one of those false color images previously, and that was Castle Lake. So in addition to Spirit Lake being, raised up, increasing its volume and area, it actually created two new lakes. So prior to 1980, Coldwater Lake and Castle Lake did not exist. In this Google Earth image, you can kind of see the maximum lateral extent, downstream extent of the debris blockage. Toes here, if you've ever been up to Johnston Ridge Observatory, this is State Route 504 that will get you up to Johnston Ridge. And then, yeah, basically the end of the Hummocks Trail is kind of like right in here. So yeah, if you're familiar, that's what we're looking at. So we went from one lake to three. And I won't go into great detail here, but in addition to managing Spirit Lake, the U.S. Army Corps of Engineers also constructed some outlets both for Castle and Coldwater Lake that do require annual inspections. My understanding is that Coldwater Lake is founded on some really good rocks, so the channel is very stable, whereas Castle Lake has kind of a similar material characterization that the debris blockage does. And so we do periodically inspect and monitor for that. Fortunately, we haven't had any events. USGS has done some modeling of Castle Lake, and from what I've been told, it's not nearly as dire a situation as a catastrophic breach of Spirit Lake. But nonetheless, we still monitor those two lakes as well. So I'd like to quickly go back to the comment I made earlier about the eruption occurring in phases. This figure from the USGS shows that there were three distinct phases of the eruption. The first was that debris avalanche that consisted of large blocks of the inner and outer edifice of the mountain. The second phase was a lateral blast in the form of a pyroclastic density current, or PDC, which was directed northward, which resulted from a large release of volatiles from the sudden unroofing of the magmatic and hydrothermal systems within the volcano. And then the third phase of the eruption was the billowing column that deposited a significant amount of ash over the top of both of those deposits. And then there were several later pyroclastic flows, I think over the course of definitely a few months, possibly up to a year, that kind of continued to slough off down the mountain, adding more fine-grained material, highly erodible material on top of that debris blockage. So the end result of that eruption essentially became an unengineered earthen dam holding back a much larger volume Spirit Lake. And because of the differentiation of material between the initial and subsequent eruptions, the resultant engineering characteristics between the debris blockage layers is highly variable, as you can see from this table that kind of shows the constituent parts of those deposits. The debris avalanche itself is dominantly heterogeneous, gravelly sand. Sorry, actually went to the wrong slide there. Yeah, heterogeneous gravelly sand, but contains silts and clays, as well as rocks that are several feet in diameter. The blast deposit consists of a lower unit of angular, unstratified, class-supported rock debris larger than coarse sand, which is overlain by an upper unit of silt to sand-sized sediment composed of ground-up bits of rock. And lastly, the ash cloud deposit is composed mainly of sand and silt. And so due to concern that rising lake levels could eventually either overtop this loose, unconsolidated material, or that, seepage and piping could potentially initiate a nick point that could then come back towards the lake, the U.S. Army Corps of Engineers, U.S. Geological Survey, and others basically said, hey, we should probably characterize this debris blockage, figure out if this is a big concern, and we probably should do something about it. So they did some early geotech investigation in the 80s to characterize that blockage. They identified the contact boundaries that you see in this diagram and elevations for each of those layers. They conducted hydrogeologic and seismic modeling to develop conservative, maximum safe levels of that lake. So those initial 1980s design assumptions and are still in place. So some of those lake levels are still founded on work by like John Sager and others from the 1980s. And so basically they said, yeah, this is a concern. So initial inundation mapping conducted by Swift and Kresh in 1983 from the U.S. Geological Survey, as well as a recent study that the USGS is currently got pending review, indicates that a hypothetical breach of the debris blockage would essentially follow the exact same path of the 1980 eruption. And so what you're seeing here on the left is just a plate that shows all of the other plates of inundation maps that were created in 1983. On the right, what you see is the inundation map for the Longview area. So down here on the left, if you've been to Longview, this is the wagon wheel in town. And anything in between these two lines is indicated as being inundated by floods. I don't know if folks online or anybody in the room can read the graph, but right about here, this indicates that the depth of the mud flow at this location, right when it comes out of the Cowlitz River Valley into Longview, would be 60 feet in depth. So very substantial. And the reason for that is there are many downstream populations at risk that include Toutle, Castle Rock, Kelso, and Longview, with a combined population of over 50,000. That 50,000 is an old statistic. I want to say it might be closer to 75,000 today, but there's a lot of people down there. And elevations determined by the hydraulic routing of the mud flow were used to prepare these maps. And essentially, it would be 60 feet of depth at Castle Rock and Lexington, 30 to 40 feet at Toutle Lake and Kelso and Longview, and 15 to 20 feet in Toledo. So obviously a very high hazard with a high potential for damage and loss of life. So not only does the 1983 and the updated modeling that's currently in review indicate that this is absolutely possible, published mapping conducted by the U.S. Geological Survey also gives evidence of prehistoric Spirit Lake lahars that definitely coincident with the 1980 eruption. But what's really interesting about this is when they go back and they look at the size of some of these lahars, the largest one was 6 times the volume of the 1980 eruption. So if we're talking 60 feet in Kelso Longview from Spirit Lake today, I mean, or back then, yeah, this thing could be pretty ugly. So it's happened before. And then, yeah, the map on the left really just does show where all the mapped lahars are, where they exist. So if you're ever driving up I-5 through Castle Rock, you can probably see some of those deposits. Shown here is just a quick table I pulled from that report that shows the model discharges and arrival times for various locations downstream that I'll show on the next slide. The key takeaway here is that a probable maximum flood, or PMF, from Spirit Lake would reach the mouth of the Toutle River 50 miles downstream within roughly 6.5 to 7.5 hours. It should also be noted that the larger population at risk downstream, including Castle Rock, Kelso, and Longview, is about 10 hours from a catastrophic breach of the debris blockage to reach that town. And so this map just shows the locations of those arrival times from the previous slide. One thing I won't touch on very much because I just didn't have a lot of time is this note here that says SRS. That stands for Sediment Retention Structure, which essentially is an earthen dam that the Army Corps of Engineers constructed in the 90s to essentially slow down the rate of movement of sediment reaching the Columbia River, because they were spending lots of money dredging and a lot of flood investments that they've made on dikes and levees throughout these towns. It was raising the stream levels and increasing the risk of flooding. So the SRS, as you can see, has really impeded a lot of sediment, and it's worked its sediment plane, pretty far upstream of the river. So if you've ever driven by, it's pretty impressive to see. But yeah, long story short, people in Longview would probably have about 10 hours after a breach to evacuate. And that's an important thing to note too, because in addition to looking at a more resilient outflow for Spirit Lake, because the Forest Service is the owner of this asset, we're responsible for letting folks know if we have an issue at the outflow that could potentially result in a breach. We have to have evacuation procedures ready to go. So we also have an emergency action plan with our partners where we communicate mobilizing response actions. But in addition to the populations downstream, there's a lot of other stuff besides the SRS. There's a lot of recreational facilities both on and off of National Forest System lands. And there's a significant amount of critical transportation infrastructure, including Interstate 5, Washington State Route 504, railroads, shipping channels, and port facilities. So yeah, it's risky. So understanding that an engineered solution would take a significant amount of time to produce conceptual designs, conduct field reconnaissance, perform geotech investigations, and provide initial through final design, and then finally complete environmental permitting, scientists and engineers understood that they needed an interim solution to manage Spirit Lake before they could construct and design the final solution. So what happened was they mobilized, they built a pumping facility, and this facility included 20 large barge-mounted 10-inch pumps that were capable of producing 110,000 gallons per minute or 245 CFS. And the pumps discharged lake water into a 5-foot diameter, 3,500-foot long buried conduit, which then entered into a stilling basin before being discharged back into the North Fork of the Toutle River. So as you can imagine, trying to mobilize this amount of equipment and supplies and build it across a devastated landscape, even just getting there, building the road to install these facilities was quite the feat of engineering that continues today. In 1982, just so happens to be the year that I was born, at the direction of President Ronald Reagan and the Federal Emergency Management Agency, the U.S. Army Corps of Engineers, in consultation with the Forest Service and U.S. Geological Survey, initiated planning to develop a long-term solution to managing water in Spirit Lake that would prevent that catastrophic breach of the debris blockage. So they looked at a suite of options. On the left are just two of the planning documents that they put together. On the right is some of the reconnaissance that they did, looking at various tunnel alignments, looking at alignments for open channels or buried conduits. And so, yeah, a few of the options they looked at were a buried conduit across the debris blockage, an open channel across the debris blockage, a tunnel, or a permanent pumping facility. Ultimately, they landed on tunnel, and the final alignment chosen was indicated here by this red circle. And that goes from the west side of Spirit Lake through Harry's Ridge into South Coldwater Creek. So if you've ever driven the road up to JRO, right before you turn that corner, you cross that creek. That bridge actually is no longer there right now because an earth flow in deposits that actually went up and over that ridge initiated, and took the bridge out. So my understanding is you won't get to JRO until probably 2027. But yeah, where was I? Yeah, so they ultimately landed on the Spirit Lake Tunnel. So in order to build this thing, they started construction July of 1984 and completed it relatively quickly in April of 1985. The construction primarily used a 11-foot diameter tunnel boring machine, or TBM, and then 3 types of tunnel support systems were used depending on the rock conditions they encountered. The entire tunnel invert, or the bottom of the tunnel, was lined with precast or cast-in-place concrete, and in good rock, which was about 55% of the tunnel, they didn't use any treatment on the walls or the crown, so it's basically just open rock. It was decent rock. In fractured rock, which was 35% of the tunnel, the walls and crown were covered with a minimum of 2-inch steel fiber reinforced shotcrete, so basically just getting across the walls, keep the spalling down. And then lastly, in sheared rock, which is the worst rock type they encountered, which accounted for about 10% of the overall tunnel, a rib set shotcrete support system was used for the walls and the crown with a 285-degree coverage on the walls and the crown. So tunneling progress when they built this thing was pretty good, with the exception of what they call the JKL. I believe it stands for Julie, Kathy, and Linda. I don't know if they were geologists or drillers, who they were, but these ladies got a shear zone named after them. So the JKL shear zone, which I'll describe in the next slide. And so prior to encountering this shear zone, their tunnel advancement rate had been 5,834 feet in 11 weeks. However, once they reached the JKL shear zone, the TBM got stuck for 2 days, and it took 4 weeks to advance the next 235 feet. So yeah, pretty substantial change in the rate of advancement for that TBM. So this figure is just a simplified geologic cross-section of the Spirit Lake Tunnel, which again was bored from the lake's west side through Harry's Ridge to outlet at South Coldwater Creek. And eventually it'll make its way to the North Fork Toutle and Coldwater Lake for that matter. The tunnel as designed ended up being 10.8 feet in diameter and about 1.6 miles in length. I won't go into a lot of detail on the geology here, but essentially the JKL shear zone is right here at a triple point where you've got a near vertical shear zone, you've got rock of two differing strengths sitting right on top of each other, dipping to the east, right in the middle of the tunnel alignment. So all of these geologic conditions combined led to that JKL shear zone. And again, you know, they did anticipate that they would hit this. They did reinforce it. My understanding was that they didn't reinforce it maybe as far as they should have. And a little foreshadowing here. I wanted to show this figure real quick just to kind of show a better map of the alignment of the tunnel, which is shown in magenta here. Again, there's SR 504, the landslide that took out the bridge, took it out right here, actually buried the tunnel outlet when it occurred, and there was a lot of concern that we may have a blocked tunnel and may need to initiate our emergency action plan. Fortunately, that wasn't the case. The tunnel cleared out the debris pretty well, but based on our post-landslide inspection, we saw some stand lines from where the debris had come up the tunnel, and it went up the tunnel like 350 feet. Yeah, so it's just really odd. You would think it would flow right over the tunnel, but it actually came back in and went up the tunnel. So pretty impressive. But the more important thing I want to convey with this slide is how we actually have to get to the intake to operate this thing. So in an emergency, we have to get across Spirit Lake. That sounds like it shouldn't be a big deal, but other than the 1980 road that has been rehabilitated after they did the pumping station and completed the tunnel, we have to take a road that has been closed for a long time. We had to rehabilitate several miles of this road to get heavy equipment, other things down. Then we built a UTV trail by hand, mind you, which every year we get these massive flows coming out of the volcano, covers this thing back up. We can't take equipment because it's in the Mount St. Helens National Volcanic Monument. So I get to take a crew of people once a year, go out and like do manual labor to clear this thing out. It's quite impressive. It usually takes a full day, but sometimes more. So then once we get down this UTV route, we then transfer into a boat, which we couldn't drive down there. We had to get it airlifted in with a helicopter. So fortunately now we have a boat, but then we get to take a 2-mile boat ride all the way out here. What's not shown on this map is the 40-acre floating log map that is subject to winds. So at any given time, those logs can be on the east side of the lake, or they could be right in front of the inlet. And driving a boat through logs of like old growth size all the way down to like, you know, small little pieces of driftwood, it's an experience. I might have some photos in this later for you to show those conditions. But yeah, that's what I wanted to show on this. So when we talk about the long-term outflow solution, for us, access is a critical, you know, component of whatever we end up deciding on for an alternative. This cross-section shows a few key pieces of the Spirit Lake tunnel design. I apologize. Water does not flow uphill. It's just kind of perspective, so understand that it's not flowing uphill. But yeah, water passes through a trash rack that is shown right here. We found that logs, as you can see here on the right, were really, where's my pointer? There we go. Logs were really impacting that trash rack. So since then, I think it was either 16 or 17, we completed a new log exclusion barrier that has a larger trash rack kind of in the outset of this excavation here. And then it's also got a flexible ring net that helps keep the logs out if the water lake level goes over that trash rack elevation. But yeah, what's important to note here is just that, yeah, we have a single fracture critical steel gate on this thing to operate, to keep the flows. We keep it open all winter long so that as we do get those, you know, typical winter storms, it can, you know, the lake level can come up, but then get out of the lake and keep the levels down. But one time we did an inspection a few years ago, and an Army Corps of Engineers structural engineer was looking at that gate and said, "Why would you guys ever get behind that thing?" And that was the impetus for a $30 million project that we're currently working on to replace this single fracture critical gate with a double redundant 4-gate system. So I could go on a lot about that project as well, but in the interest of time, yeah, we don't have it. So. All right. So in 2014, like everything was going great since 1985, for the most part. There's a few repairs in here that I don't mention, but I'm bringing up the 2016 one because this was the big one. So all was going good until a inspection in October of 2014 indicated a need to repair a heave in that JKL shear zone. The figure on the right shows geologic mapping from original construction and the approximate extent of that heave. The heave began long ago due to high ground pressures, the weakness of the shear tuff dipping beneath the tunnel, the adverse orientation of fractures in the basalt, and the absence of those steel rib sets that I mentioned earlier. So for several years, the amount of heave remained very steady at about 24 inches. The distress was limited to the tunnel invert, so we didn't see anything on the walls or the crown. It literally was just coming up off of the floor. So then, during the October 2014 inspection, we noticed an additional 18 inches of heave. Existing cracks in the cast-in-place concrete invert showed that there was severe dilation. Again, the walls and crown, no distress. But a follow-up inspection in April of 2015 revealed an additional 4 inches of heave. And so what ultimately resulted was the tunnel diameter had been reduced from that 10.8 design diameter to 6.8 feet, which is shown on the figure here on the left. So the ramification of having a narrower tunnel or a smaller diameter tunnel is that we can no longer operate that at maximum design outflow capacity, which if we have a very significant hydrologic event in the Spirit Lake Basin, it could exceed our ability to pass that thing through the outflow. Yeah, and I think our current, I think the original design capacity was 550 CFS, and we're currently at 64% of that, around like 350 is our maximum opening that we can have at the gate. So then Congress got involved. This is really when the agency started making a lot of moves to get some things done. So on September 24th of 2015, we received a letter from Representative Jamie Herrera Butler, Senators Patty Murray and Maria Cantwell, directing the Forest Service, Army Corps of Engineers, and US Geological Survey to develop a long-term resilient solution for management of lake levels, which led again to significant agency efforts to establish baseline information and initiate that planning. The Forest Service requested the National Academies of Science, Engineering, and Medicine to convene a committee to help develop a decision framework, because I won't go into a lot of the politics behind this, but there are a lot of interested parties, a lot of regulatory management, a lot of private interests downstream of National Forest System lands. So ultimately, the Forest Service has the sole responsibility of making a decision that impacts 1 million people who have 1 million opinions on how this should be managed. So I won't get into it too much, but that's what NASEM, or the National Academies of Sciences, Engineering, and Medicine, helped us figure out. And they gave us this decision framework for managing Spirit Lake. If you ever want to know more than you ever care to know about Spirit Lake, this document, and then this one here by Gordon Grant and John Major, and I apologize, I forget the third off the top of my head, I think Sarah Lewis maybe, are very comprehensive about Spirit Lake and the debris blockage. So yeah, more information, highly recommend those documents. But yeah, this was the impetus for us to start our planning. So that's what we're currently doing now. And our project objective is to create a long-term outlet configuration that removes that threat of the catastrophic release for Spirit Lake. So we call this the Spirit Lake Outflow Safety Improvement Project. I just like to refer to it as SLOSIP because it's a lot easier to say. So yeah, we started that in 2020. We awarded a $2 million contract to prepare an environmental impact statement to comply with the National Environmental Policy Act. For those of you who aren't familiar with the National Environmental Policy Act, it essentially requires federal agencies to determine if their proposed actions will have any significant environmental effects. So yeah, again, some of the objectives for this was that, number one, we need to maintain those lake levels at the safe operating level. We need to be able to accommodate water level rise from a intense hydrologic event. We also need to have good, reliable access, which we currently don't have. It's very hard to commission a helicopter in the Forest Service if you're not a firefighter. And lastly, we need to have some level of redundancy so that if we do have one of the outlet options fail, we can work on a second one while we repair the first. So that's kind of where we're headed with this. Apologize, I don't really like texty slides. This is very texty. I'll get into the pictures about this, but basically we conducted, through one of our sub-consultants, they conducted a feasibility study that builds upon a progression of studies and reports that the U.S. Army Corps and others produced in the 80s and 90s. They considered several outlet options. Some of these are still there. So previously I mentioned a buried conduit. I talked about a permanent pumping station, talked about an open channel. All those were kind of carried forward. And the NASEM Commission also identified a few options that should be considered for long-term management of risk. So again, apologize for the wordy slide. I'll actually describe these in a little bit more detail in the following slides. So the National Environmental Policy Act requires a no action alternative be analyzed to show how doing nothing would fail to meet the purpose and need of any federal project, which in our case is again creating that long-term resilient outflow that removes that potential threat. So by doing nothing, essentially we're telling the public that we wouldn't be able to do that. We can't reduce your risk if we don't do anything. We have to do something. And again, the no action alternative also gives you a baseline to compare effects. So like what would the effect of not doing anything be on the community versus what you're planning to do? So alternative 2 is the major repair option. This is a full rehab of the existing tunnel, including enlarging that constricted JKL shear zone to restore our full tunnel capacity. The shear zone would be using the same methods that they used before to repair those rib sets, and they would just extend that out. Alternative 2, coincidentally, does not include a redundant option. Alternative 3 is a minor repair option that would focus only on that JKL shear zone, and it would construct a buried conduit across the debris blockage. So essentially, if you think about like a box culvert, concrete box culvert, it would just be buried and connected across the debris blockage. That would be the redundant measure. And then that essentially would follow the existing path of the old disturbed area from the 1980s pumping station. So alternative 4 is to convert the existing tunnel into a pressure tunnel. Essentially the difference between a pressure tunnel and a gravity tunnel is that a pressure tunnel you can control the bottom, you can fully fill the tunnel and pressurize it. So it allows you to get, number one, higher discharges, and we could access it from SR 504. So that accessibility is a major consideration for us. In addition to those considerations, it also would lower the intake level, which would then also allow us to lower Spirit Lake below 3440. And the reason we're stuck at that 3440, as I showed the inlet earlier, that excavation is actually graded towards the lake. And so that maximum elevation before it gets into the intake is 3440. So by putting in the pressure tunnel, we could excavate that out, lower the intake slightly, and we could lower the lake a little bit more to buffer those intense hydrologic events that could come in. Yeah, there's a lot of other considerations that I won't go into great detail. Yeah, the log mat, though, is one of them. So anything that goes into a pressure tunnel has the potential to do catastrophic damage. So yeah, it would take a lot of work on the front end to make sure we don't get anything going into the tunnel. So alternative 6 is that large open channel that would maintain Spirit Lake at its current operating level of 3440. Based on preliminary alignment, it looks like this open channel would be 6,450 feet long with cut slopes up to 250 feet vertical. Yeah, massive, massive cuts in what is presumably very unstable material that has not been characterized. So yeah, a lot of unknowns on that one. But the benefit of this measure is that channel flow capacity would scale with lake level and really is only limited by channel dimensions. So rather than having to worry about the lake level rising, the lake would just flow out even if we do get those extreme events, much like a natural river system would. Yeah, the channel would most likely, well, would require channel bed reinforcement to provide that erosion resistance to prevent a nick point from coming back up, retrogressing and releasing the lake. So here's the really big one, Scott. Channel construction would excavate 11 million bank cubic yards, which would result in 22 million loose cubic yards. That's enough to fill Spirit Lake. And where do you put that much stuff? And how do you, in just the infrastructure to haul it out, that heavy haul equipment, you need a massive, beefy road. And yeah, we don't have a location where we would put it. So we are still considering this option. It is viable, but yeah, obviously a lot of things to consider before we could do that. Yeah, and then the backup for this one would be that we would use the existing tunnel as that backup. So if for some reason, you know, that channel failed, or like, let's say there was another lahar that blocked it, a debris avalanche that brought us back to the same situation, we would still have the existing tunnel as an alternate. All right. Yeah, so then alternative 7 is a natural channel development. We would include a new pressure tunnel, which would follow the existing alignment of the current tunnel. The reason being is that it's already been well characterized. We understand the geology really well, so that is like an ideal location to put it. And then we could use the existing tunnel as a backup as well as access. And the interesting thing, our consultants kind of came up with this in talking with some of the folks that are on one of our collaboratives. Colin Thorne does a lot of sediment modeling, kind of pitched this engineering with nature idea. But essentially what you could do is there's a series of depressions across the debris blockage. And if you were to initiate, some natural channels to kind of connect these, you could potentially, with the use of a siphon, put water through this, controlled over time to kind of slowly start initiating a natural channel. And you would still have, again, your pressure tunnel and existing tunnel as a backup outlet. So on the right here, this is just an example of a siphon system. It's like Boardman River dams. So yeah, that's alternative 7. Alternative 8 is a buried conduit option. However, this one is a little different in that the idea would be you could install this buried conduit using the existing tunnel as the backup. And over time, you could release water out of the end of that conduit. As the erosion from that flow coming out of the end of the conduit stabilizes, you could then excavate that next upstream section of conduit, remove it, allow it to do the same thing, controlling those flows. And so you could stage letting hydraulic excavation work naturally in your favor. The obvious ramification of this is that all of that sediment from that debris blockage that you hydraulically excavate out, where does it go? Right down to the Columbia River. So yeah, that is alternative 8. Lastly, alternative 9 would basically reevaluate the debris blockage stability by conducting updated geotech investigations that would gather data in support of updating groundwater and seismic modeling. And if the results of that updated modeling indicate that conservative design assumptions made in the 80s are no longer valid or just didn't come to fruition, then it may be possible to increase the maximum safe operating levels at the lake, thus increasing the storage buffer to accommodate those extreme hydrologic events. However, this would require a complete redesign of the current intake structure. And yeah, we may have to do additional stabilization at some of the critical low points, which are shown on the right here, critical point north and critical point south. This LiDAR image just shows the lake level if we were to raise it up to 3480, which is currently 40 feet higher than our current operating level. And then this image put together by our contractor just shows, yeah, most of these options. So again, here's the south shore of Spirit Lake. Mount St. Helens is just to the south off of this image. The crater would be somewhere kind of down towards the bottom of the page. This shows the open cut, those 250-foot high excavation slopes where we could potentially put some engineering with nature type things. This road is the one that we actually completely rebuilt as part of that $30 million intake gate replacement project. So this was just completed this summer. So it currently exists, but our previous NEPA indicates we will reclaim that. So the jury's still out on what we're gonna do with that road, I guess. So yeah, moving on. I'll kind of quickly breeze through the last of these because I realize I'm almost at time and yeah, don't want to belabor this too much, but when you're thinking about any of these alternatives, there's a number of risks that you have to consider, including natural hazards, construction risk, outlet performance, any environmental risks, which again, we might elucidate in the environmental impact statement. There are obviously implementation risks, which are unintended consequences requiring future mitigation. And we decided to pull sediment mobilization out of the environmental, and I'll talk a little bit about that when we get there. But natural hazards include all the processes that could be reasonably expected to occur on the flanks of an active volcano, including those initiated from extreme hydrologic events, geologic processes, including local and regional stresses, mass wasting events, volcanic processes, and seismic, whether local or regional. And one major consideration for an open channel alternative is that, again, nick point. So yeah, retrogression is a serious issue with a natural hazard. And lastly, top photo at the right kind of shows an example of that highly erodible material at the Truman Channel. So this is debris blockage that has been eroded since 1980. And the bottom right just kind of talks about some of the considerations you may have to take into account for those open excavation cuts, like ground reinforcement, groundwater conditions, et cetera. As indicated on this slide, any of these construction risks could lead to significant increases in overall project costs, which underscores, in my opinion, the critical importance of a thorough surface and subsurface site characterization program. If you guys in your future career ever get pushback on how much you want to spend to do a geotech investigation, just remind them of some projects. You'll find them about when they didn't do it right, how much it ended up costing them. So always push for more than you're going to get approved for. Where was I? Yeah, so given the time frame required for such a large cut, it could take multiple seasons to complete construction, and you'd have to winterize the site, so you'd have to pay really good attention to ensure that critical measures are put in place to not lose your previous work that's been done in a mountainous weather environment. Regardless of the option chosen, they all have trade-offs and performance measures. For example, an open channel would obviously be more vulnerable to the existing tunnel. An open channel would obviously be more vulnerable than the existing tunnel to a debris flow initiated from the crater of the volcano. A tunnel bored in competent rock might be less prone to damage. Sorry, I'm losing my spot here. During a seismic event that would cut slopes in an open channel. And yeah, a pressure tunnel configuration with outlet valves located near the current outlet would be way easier for us to access than the existing gate control inlet. However, with increasingly complex systems, there's more maintenance, there's more costs. So every consideration, every risk has a trade-off. And to balance all of these for a project of this magnitude is definitely tricky. Again, talking about NEPA, if any of you end up working for the federal government, you will do NEPA. The agency is required to disclose those impacts. And so additional resource considerations that are not listed on this slide include impacts to wildlife, socioeconomic impacts on local communities from the project either occurring or not occurring. And so, yeah, lots of things to consider in the environment. Implementation risks, obviously, I didn't talk much about it on this talk, but the NASEM committee, again, identified several federal, state, local jurisdictions that would be impacted by any alternative we choose. Again, everybody's going to have an opinion. And balancing risks and trade-offs to all of these stakeholders and the resources that they value most is an incredibly challenging task. And I'm really glad that I don't have to actually make the decision on which alternative is going to be chosen. Yeah, sediment mobilization, I'll just very briefly touch on. The reason this is so important is that the forest boundary of the National Volcanic Monument is only 10 miles downstream from Spirit Lake, where it then transitions into state and private ownership. And the U.S. Army Corps has that sediment retention structure. So anytime you propose a federal project that could impact their investment, whether that's a dam, whether that's flood control levees, you have to go through the Section 408 process. And basically what that entails is you give the Army Corps of Engineers a 95% level design, then they tell you whether or not you can do the project. And they have the sole authority to do that. So sediment mobilization for downstream infrastructure, not only for the Army Corps, but the communities downstream is incredibly important. I talked a little bit about one of the other ongoing projects that we have, that $30 million intake gate replacement project. This just shows a schematic. This is a plan view. This is an elevation view showing those two flow paths with a redundant gate for each path. And then the image on the right just shows that 1980s access road, we call it the Truman Trail, that we kind of reestablished. We're actually building a barge loading facility, much like they did in 1980, to then create a coffer at the inlet, dewater it, do the construction for the gate. And yeah, that should be completed in FY27. So that was a lot. I thank you all for bearing with me, and I'd be happy to take any questions you might have.